Imagine standing under a clear night sky. The stars are steady, a patient pattern that has watched us for millennia. Far above, everything seems fixed constellations, myths, invisible grids we once used to cross oceans. But in the quiet, tiny things keep changing. The solar system breathes. It trades pieces with the galaxy. And sometimes, one of those pieces steps over an invisible line and never returns. Astronomers call these departures interstellar, not poetic metaphor literal physics. To be interstellar is to be unbound, to slip the sun's grip and head for open space. In 2017, we met our first true interstellar visitor, 1I Oumuamua, which brushed by, surprised everyone, and left its share of lingering puzzles. In 2019 came 2I Borisov, a more classic comet with a dusty tail and familiar chemistry, except for one essential twist. It wasn't from here. And then there was 3I-ATLA. 31ATLAS is the interstellar visitor that breaks the rules. It moves like a foreign guest, skimming through our system on a hyperbolic path. Yet, by all the best evidence, it wasn't born in another star's nursery. It seems to be hour-shaped by our own sun, tugged by our own planets, quietly escorted to the door by Jupiter, and shown the way out. Interstellar, yes. Alien, no. If you were to zoom out and watch the solar system as a slow-motion ballet, Jupiter would stand out as a giant dancer with a powerful reach. A small rock passing near that giant can gain or lose astonishing amounts of energy, stealing a sliver of Jupiter's orbital motion. This is the physics of gravitational assist, the same technique engineers use to send spacecraft to the outer planets with relatively small fuel tanks. Nature used it on 3I-ATLA. The object approached, was turned, speeded, and flung onto a path that no longer circles the sun. Not a loop anymore, but an open curve, a hyperbola. That single shift from a bound ellipse to an unbound hyperbola matters. It's how astronomers formally decide whether an object is interstellar. If, in a frame of reference centered on the solar system's mass, the barycenter, the object's energy is positive, it won't return. That is the line. Cross it, and you're an interstellar object. Here's the first quiet surprise. Most of us imagine interstellar objects as emissaries from other suns. But dynamics only cares about energy and trajectory, not biography. By that standard, 3I-STLAS qualifies. An interstellar traveler set loose from our own home. The Minor Planet Center, which handles the catalogs and names, gave it the 3I designation after follow-up observations determined its escape was real. Another gentle surprise. 3I Atlas appears to be inactive, no obvious tail, no glowing coma. That doesn't make it unique. 1I Oumuamua looked similarly quiet in ordinary images. But it does make it a compelling link between categories. Comets can go dormant. Asteroids can hide ice. Some small bodies are mixtures of rock and volatile ices in complicated textures, like cosmic granola bars frozen for billions of years. The surface is the only part we see, and silence at the surface can hide a noisy interior. And then, a third detail, easy to overlook but powerful. When astronomers integrated 3I-ATLAS, his orbit backward in time, running the solar system like a planetarium, projector in reverse, they found that before it passed near Jupiter, it had been bound. Not by much, perhaps, but enough. It wasn't diving in from interstellar space to pay a visit. It was climbing out from our own backyard when Jupiter nudged it just a bit harder, enough to push it past escape. As you listen, you might picture a small pebble of darkness, perhaps 100 meters wide, perhaps more. Not reflective, not flashing. Just a dim moving speck on a CCD image, a few pixels above the background sky. The telescopes that trace at Atlas, Pan-STARRS, and others scan the sky every clear night. They aren't designed for poetry, but there's something quietly poetic in what they reveal. The solar system is not a closed box. It leaks, it exchanges. It's connected to everything else. So the story of 3IA2LAs begins with a gentle paradox. How can an object be interstellar and yet not foreign? How did we miss it on the way in and only meet it as it left? And what does this subtle case tell us about the rules we thought we understood about comets, asteroids, and the gravitational architecture that holds everything together? We'll trace the path, the surveys that found it, the math that named it, the evidence that suggests its birthright was local, and the broader implications for how planetary systems like ours grow, share, and shed their material. The mystery isn't dramatic. It doesn't need to be. It's a calm unraveling of definitions and boundaries, a reminder that in a universe of motion, labels often lag behind behavior. The pebble is already on its way into the galactic night, but it leaves behind a quiet question. What else will we see differently now that this door has been noticed? To understand 3I Atlas, it helps to revisit the short history of interstellar visitors that announced themselves in the past decade. Each one changed expectations, and together they set the stage for this third, rule-bending member of the family. The first 1I, Oumuamua, was discovered in 2017 by the Pan-STARRS survey in Hawaii. It moved too fast and on to open a path to be bound to the sun, a clear hyperbola. Yet it didn't behave exactly like a comet. No visible coma or tail was seen, even with sensitive instruments. As it receded, it showed a small non-gravitational acceleration, something pushing it very gently, as though gas were venting from its surface or sunlight were interacting with an unusual shape. Its light curve suggested an elongated object tumbling, though the details remained debated. Oumuamua demonstrated something subtle and thrilling. Space between the stars is not empty. Other systems eject debris, and some of it passes through. 2 years later came 2I Borisov, found by amateur astronomer Gennady Borisov in 2019. This one looked like a textbook comet. It displayed a coma and a tail, and spectra detected familiar molecules like CN and C2. There were hints of unusual chemistry, for instance, high levels of CO relative to water in some observations, implying it formed in a very cold region in its system of origin. Borisov showed the other end of the spectrum, clearly interstellar and clearly cometary, an icy messenger that behaved, in broad strokes, like comets we knew, just born elsewhere. Before these, hyperbolic comets were usually imposter solar system comets whose orbits appeared slightly unbound because of subtle forces like outgassing or small errors in short data arcs. The hallmark of a true interstellar object is robustly positive energy relative to the sun, after accounting for planetary tugs and, ideally, a trajectory that was already unbound before entering the planetary region. That last part matters. A comet can be kicked into an apparent hyperbola by Jupiter, but that doesn't mean it came from another star. Enter 3IATLAS, discovered by the asteroid Terrestrial Impact Last Alert System Atlas. This sky survey uses small, wide-field telescopes to scan the heavens nightly, looking for moving points of light that shift slightly between exposures. The software flags candidates. Humans and additional telescopes provide follow-up. It's a quiet, systematic effort. Image, subtract, compare, repeat. Many discoveries are simply more pieces of the asteroid belt or long-period comets returning after millennia. But some are stranger. Atlas found an object moving in a way that, when the early observations were fit to a path, suggested a hyperbolic orbit. It was outbound. No desk-thumping excitement. Just a realization that this one wasn't coming back. Further measurements from other observatories tightened the orbit. The Minor Planet Center, which curates the data and issues designations, ultimately announced it as 3I Atlas, the third officially recognized interstellar object. Here is where the quiet controversy entered. Astronomers quickly noticed that when they integrated 3I-ATLA's orbit backward, taking into account the gravitational fields of the planets, the trajectory did not look like a classic interstellar inbound. Before a close interaction with Jupiter, the object had been on a bound, likely long-period orbit. The implication was straightforward. 3I-ATLAS was one of ours, nudged out by our largest planet. It became interstellar, not because it was born under another star, but because Jupiter opened the door and let it go. This distinction invites a gentle refinement. There are at least two useful categories: extrasolar interstellar objects, Oumuamua and Borisov born under other suns, and solar system-born objects that become interstellar, like 3I Atlas after a gravitational slingshot. Both meet the dynamical definition of interstellar, but their origins and what they can teach us differ. Several unusual facts tend to surprise even seasoned skywatchers. Jupiter likely ejects enormous numbers of objects over the age of the solar system. Computer simulations show that the giant planets, especially Jupiter and Saturn, are efficient at stirring and eventually expelling small bodies from the outer solar system. Many comets we see are on their way in. Many more leave forever. The distinction between heliocentric and barycentric orbits matters. Near a giant like Jupiter, paths measured relative to the Sun can appear erratic. To decide whether an object is truly interstellar, astronomers compute its energy relative to the solar system's center of mass and trace it before and after planetary encounters. A quantity called the Tisserand parameter with respect to Jupiter acts as a rough fingerprint for how an object interacts with that planet. It's not a perfect invariant, but it helps separate different dynamical families. Objects that can be strongly scattered by Jupiter tend to show characteristic Tisserand values. 31-ATLAS fits patterns that mark it as having been in Jupiter's dynamical grasp. This is a calmer kind of detective story. The clues are not dramatic images, but columns of numbers. Right ascensions and declinations, brightnesses, times. The plot twist is a refined orbital solution and a realization that the lines drawn on the sky point to a homegrown origin. The telescope domes in Hawaii, in Chile, in the Canary Islands, slide open with a low hum. CCD's cool. Observers sip coffee and watch for points that move. Somewhere between these small nightly rituals and the patient arithmetic, 3I-ATLAS slipped from unknown object to the third interstellar to the first interstellar that was ours. If that seems like a technical nuance, it is. But it's also a reframing of how planetary systems live. Interstellar space is not just a highway for foreign visitors. It's the ocean our own ships eventually enter, sometimes without sails, pushed only by gravity. And 3i Atlas is a little ship like that, unadorned, probably quiet, a silent stone that crossed a boundary and kept going. To go deeper, let's slow down with the physics. How do astronomers know whether an object is truly leaving the solar system? And how can they tell where it came from? They begin with observations, time-stamped positions against the background stars. String enough of these together, and you can fit an orbit, a curve that best matches the data. Early fits can be misleading. The sky is noisy and arcs are short. But as hours become days and days become weeks, the path sharpens. For 3i Atlas, the refined fits showed a hyperbolic trajectory when expressed in a barycentric frame. That word barycentric just means we're measuring motion relative to the center of mass of the entire solar system, not just the sun. In this frame, gravitational nudges from the planets are properly accounted for. Next comes integration, numerical stepping of the orbit backward and forward in time, including the gravitational pulls of the sun and planets. This is like rewinding a film, frame by frame. If, before a close approach to Jupiter, the computed orbit settles into a bound ellipse around the sun, the object belonged to us. If it approaches from far away with a substantial inbound speed that cannot be captured by our sun's gravity alone, it came from elsewhere. For 3i Atlas, backward integrations by independent teams showed that before a recent close encounter with Jupiter, the object's orbit was bound loosely, more like a long-period comet than a tight asteroid belt rock. Past that encounter, the energy was positive. The transition was Jupiter's gift, a gravitational assist. You can visualize it. The object approaches the giant planet. In Jupiter's frame, it whips around and departs with the same speed. But in the Sun's frame, Jupiter is moving. That motion permits a swap of energy. The small body leaves with a bit more speed relative to the Sun, sometimes just enough to crest the ridge of escape. There are other diagnostic tools, too. Astronomers often compute the Tisserand parameter with respect to Jupiter, a quantity derived from orbital elements that stays approximately constant during some types of gravitational interactions. It helps classify whether an object is in the realm of Jupiter family comets, long-period comets, or can be strongly scattered into hyperbolic escape. For 3i Atlas, the Tisserand analysis pointed toward a history compatible with Jupiter's influence, not an inbound path from interstellar space. What about the object's physical nature? Here, the data are gentler and more tentative. Observations in reflected light suggest that 3i Atlas is not strongly active. No obvious coma or tail was detected in typical images. That immediately places it in a curious category. Inactive comets exist bodies with ice beneath a crust hardened by time. Asteroids can also be dark, carbon-rich, or surprisingly reflective, depending on surface texture and composition. Without a tail, sizes must be estimated from brightness and assumed reflectivity. The numbers are fuzzy, but the picture that emerges is a small object, likely tens to a few hundreds of meters across, a cousin to many near-Earth objects that pass by unnoticed. The absence of a visible coma does not settle its identity. 1i Oumuamua also lacked a typical coma, yet showed a minute non-gravitational acceleration that could be explained by very low-level outgassing, or, in some models, by a thin layer of volatile ice being warmed. For 3IATLAS, no such acceleration has stood out clearly. The observational arc was sufficient to nail down the escape, but may not be long or precise enough to detect subtler forces. It is possible that 3I is simply rocky. It is possible that it is a cometary nucleus that never warmed enough to display activity on this pass. In a sense, this uncertainty adds to the calm intrigue. The most decisive evidence in this case comes from dynamics, not chemistry. Three details particularly enrich this diagnosis. Inbound asymptote. For a true extrasolar interstellar object, when you integrate backward far from the planets, the object approaches with a measurable asymptotic speed. The hyperbolic excess velocity, v infinity, inbound. For 3IATLAS, solutions indicate that before the Jupiter encounter, that value was effectively near zero in the barycentric frame consistent with a bound orbit. That's a technical way of saying it was not plunging in from interstellar space. Ejection efficiency. Simulations of the early solar system suggest that giant planets eject an enormous mass of small bodies over time, likely more mass than remains in today's asteroid belt. Most planetesimals formed beyond the snow line never settled into permanent orbits. They were stirred, scattered, and expelled. 31ATLAS offers a present-day snapshot of that long, quiet process still in action. Observational bias. Surveys like ATLAS and PAN-STARRS are tuned to find moving objects that are relatively close and bright enough to see. A small, dark object from interstellar space might only become visible near perihelion and then slip away quickly. A small, dark object from our own solar system on a long-period path may look similar. With limited observing time, a faint, outbound object like 3I Atlas can be studied enough to define its path, but not enough to paint a detailed portrait of its surface. This practical limitation shapes our understanding. In a reflective light, 3IATLAS becomes less a puzzle to solve and more a mirror. It shows us the boundary conditions of our definitions. We like crisp categories: comet, asteroid, interstellar, solar system. Nature serves gradients. The physics of gravity is continuous, and so are the labels we place on it. What the object teaches gently is that a name like interstellar can describe a state as well as a story. And sometimes the state changes while the story stays here. Imagine once more the observational scene. A screen in a control room. The object appears as a speck, shifting slightly over minutes. The coordinates are recorded, precise numeric notes in a universal language. Someone cross-matches catalogs, requests follow-up, pings colleagues. And all the while, 3I Atlas glides outward at a pace you could never see with your eyes alone. No drama, yet something quietly momentous has happened. Our solar system has released a small piece of itself to the galaxy. What else gets carried out in such departures? Ice, organics, dust cemented into pebbles. And if every planetary system sheds material, how much of the dust between stars is made of long-ago visitors, now untethered and uncounted? The next part of our story widens the frame, tracing that shared ocean and the far shore implications of an object that leaves rather than arrives. If 3IATLAS is the first interstellar object we've caught that likely started here, then it is also a landmark in a broader, quieter exchange. What planetary scientists sometimes call the galactic traffic of small bodies. To see its place in that flow, think of our solar system not as an island, but as one port among billions along a dark sea. From the earliest days, our system was busy with trades. In the protoplanetary disk, tiny grains stuck together, snow lines formed where ices could survive, and planets accreted by gathering nearby material. Giant planets, once born, sculpted the rest. They carved gaps, stirred orbits, and scattered leftovers. Some leftovers were launched outward into the distant Oort cloud, a vast reservoir of comets that may reach a quarter of the way to the nearest star. Some were kicked inward and consumed by the sun, or collided with worlds in the making. But a great many were ejected entirely, their energy lifted above escape, sent drifting between stars. Most systems likely do this. In the big picture, ejection is not a rare curiosity. It's the rule. 3 gently surprising ideas can anchor this cosmic view. The galaxy is seeded with planetesimals. The total mass ejected by typical planetary systems over billions of years may be enormous. Models suggest that the space between stars could be sprinkled with trillions upon trillions of objects the size of comets and asteroids. Only a tiny fraction will ever pass near enough to a star like ours to be seen, and even fewer will be bright when they do. But their existence is a natural consequence of how planets form. Ejection is a two-way exchange. While our system sends material outward, it also receives. Long-period comets from the Oort cloud may include objects captured from other stars when the sun was young, still in a cluster where stellar neighbors passed close by. Even today, extremely slow interstellar dust grains and rare small bodies can be temporarily ensnared. The borders are porous and dynamic. Definitions shape our expectations. Before 3I Atlas, interstellar in popular imagination meant from another star. That picture remains. Useful it describes Oumuamua and Borisov well. But dynamical definitions remind us there's also an interstellar by departure category, objects that cross the energy boundary on the way out. Recognizing both helps us plan searches, design follow-ups, and interpret statistics. Analogy helps here. Picture a riverport. Boats constantly arrive with goods from far inland, and others depart, some even built at the dock and pushed downstream. If you're recording traffic, both arriving vessels and outgoing vessels pass the same buoy that marks the edge of town. A logbook might simply count boats crossing the boundary. If you want to know about distant cities, you'll track inbound boats, what they carry, how they're built. If you want to know about your own shipyard, you'll track outbound ones. 3-1 Atlas is an outbound boat. Counting it tells us something about our shipyard. How many such departures should we expect to see? Upcoming surveys promise answers. The Vera C. Rubin Observatory, formerly LSST, will begin wide-field operations soon, scanning much of the southern sky every few nights with sensitivity far beyond current surveys. Rubin is projected to find interstellar interlopers at a rate of perhaps 1 every year or 2, potentially more, depending on how abundant they truly are and how reflective they tend to be. Some will be inbound extrasolar visitors, like Oumuamua or Borisov. Some will be outbound locals new 3I cases. The precise mix will tell us about both the galaxy's supply and our solar system's current ejection habits. Another instrument, NASA's NEO Surveyor, optimized for infrared detection, will add a complementary ability, measuring thermal emissions to estimate sizes more robustly. A key frustration with optical observations is the ambiguity between size and reflectivity. Dark objects can masquerade as small bright ones. By catching heat, NEO Surveyor will reduce that uncertainty. For objects like 3IATLAS, it could help distinguish a small, dark, rocky body from a slightly larger, more reflective one, and provide better constraints on whether low-level activity is present. A few additional details, often overlooked, deepen the stakes. Many known hyperbolic comets in historical catalogs were later recognized as solar system comets with slightly mismeasured orbits or non-gravitational accelerations from outgassing. That is why modern standards for declaring an object interstellar are careful. Robust measurements, barycentric calculations, and, when possible, the inbound context. 31ATLAS passes the dynamical test without needing to invoke delicate outgassing models. Jupiter's role as a cosmic bouncer is not evenly distributed. The geometry of encounters matters. How close, at what angle, and on which side of Jupiter the object passes. Only a narrow set of paths leads to escape. Many other interactions merely reshape an orbit. That 3I Atlas found one of those exits reminds us that, given enough objects and time, the improbable becomes ordinary. Classification guides strategy. If we capture, say, 10 interstellar objects in a decade, and half are outbound locals, that tells us our present-day ejection rate is measurable in real time. It also argues for early follow-up. A small body discovered outbound is already fading, and the window for spectroscopy or deep imaging can be short. Knowing which to prioritize can extract more science from limited nights. As you picture all this, keep the tone unhurried. The river flows even when you're asleep. Rubens' dome will open and close in a rhythm that soon feels like breathing. The archives will fill with dots and curves. And among those, every so often, will be a path that crosses the boundary once, leaving behind a new line in a ledger, interstellar. Some of those lines will mark foreign guests. Some will mark locals departing. The difference is quiet, but it carries meaning. There is also a human rhythm. We like to sort and name. We like to tell stories about edges, when something becomes something else. 31ATLAS gives us a chance to refine that story without hurry. We can keep the designation, it's informative, and add context in how we talk about it. Interstellar, but not alien. The object broke no laws. It simply showed us that our rules were narrower than the sky. What might it tell us about materials? If it is an inactive, rocky body, then ejection is not limited to icy comets. If it is an ice-rich nucleus that happened to stay quiet, then dormancy is more common than we thought, and some interstellar travelers might carry fragile molecules that never get exposed. Either way, 3IATLA nudges us to expect diversity among both inbound and outbound crossers. A population with many shades will require gentle patience to understand. Let's bring the story to rest. The sky above is still. The telescopes are cooling. Somewhere beyond Jupiter's orbit, 3I Atlas is already farther than when we began. The sunlight on its surface a little dimmer, the stars ahead a little brighter. It will not come back, but the meaning it leaves behind lingers. The deeper thread is about boundaries. Physics draws one that is wonderfully crisp. Bound versus unbound, negative energy versus positive. Cross that line, and your fate changes. But human categories are softer. We use words to describe how things feel familiar. Foreign, comet, asteroid, visitor, native. 31ATLAS shows how these layers interact. Dynamically, it is interstellar. Historically, it is ours. Both statements are true. Together, they open a useful door in the mind. They also remind us that our system participates in a galactic economy. Material flows outward, and material arrives. Most of the time we don't see it. Now and then, with the aid of quiet machines and careful arithmetic, we do. The ejection of a small stone by Jupiter has the same logic as a spacecraft's gravity assist, a routine application of celestial mechanics that feels almost like a courtesy, a hand on the back, a gentle push toward the next stage. The science deepens into three reflective motifs. Exchange is a natural outcome of growth. Planets do not form without stirring their surroundings. Scattering is not an accident or a waste. It is a symptom of the system's vitality. The thousands of ejections across billions of years are the invisible balance sheet that allowed the survivors' planets, moons, belts to settle into the patterns we see now. The galaxy is built from shared leftovers. Interstellar space is not sterile. It holds dust, pebbles, and sometimes house-sized bodies, carrying the chemistry of whatever kitchens baked them. Perhaps a fraction of the organic molecules that seed young worlds began as fragments cast off by others. Perhaps some of our own dust will someday fall into a distant nursery, a whisper of our past becoming part of someone else's beginning. Perception evolves with capability. Atlas, Pan-stars, and their successors expand our senses. Vera Rubin's cadence will make the sky feel alive in a new way. Neo-Surveyor will add heat to our maps of light. With each step, more of what has always happened becomes visible. 3-1 ATLAS is not strange because it exists. It is notable because we noticed. There is also a small, humane lesson. Many wonders are quiet. 3-1 Atlas has no tail that arcs across the sky. It is not bright. You could pass a lifetime looking up and never know it was there. Yet in its modesty, it touches big ideas. What it means to belong, how boundaries are crossed, how definitions adapt. Interstellar, but not alien. Leaving, but teaching as it goes. So what next? Soon, we will likely meet more of these boundary crossers. Some will arrive glowing and shedding, their spectra revealing ices we've never seen. Some will depart barely brighter than the background, noticed only by careful software and patient follow-up. Each one will add a stitch to a tapestry that joins planetary systems into a larger whole. If you step outside after this, the night will feel the same. The Big Dipper will still hang where it always does. The moon will go about its phases, and the quiet will be complete. But perhaps you will feel a new softness around the word interstellar. It no longer marks only the far and foreign. It also marks a moment in a journey, a threshold crossed by a pebble of our own making, guided by the clockwork gravities of our own home. Thank you for listening, for letting curiosity be soothing rather than urgent. If you'd like more calm stories like this science, told at a gentle pace, with room to wonder, you're warmly invited to subscribe to Hypnosphere. We'll meet again under the same sky, and somewhere out there, another small traveler will be crossing another quiet line.